So, shall we start? So, good afternoon, everybody. Her Excellency, colleagues, friends, it's a pleasure to have you here today. We are back finally to a real event. I mean, we have been, for 2 years, we have been attending these events, the Fermi lecture online. And after these 2 years, we are finally back in this new space, new location that the Institute has been completing a few weeks ago. I will immediately give the floor to the Italian ambassador, because I think that it's important. This is co-organized, as you know, between the Institute and the ambassador. Unfortunately, our president cannot be here this afternoon. This morning it has been called, I think, for engagements related to the COP27, and most of you know that we are engaged in the process with the Republic of Cyprus in submitting this huge plan. Most of us, we've been working in these months on the East Mediterranean and Middle East area. So he will not be with us, so I will not take so much time now. And I would invite the Italian ambassador, Ferrari Bravo, to have a short speech, and later on I will introduce our guest, our lecturer.
Good evening, everybody. I'm very pleased to be here today with you. As you know, Fermi lecture is one very important theme of our scientific diplomacy initiatives. Scientific diplomacy initiative and means a project that the Ministry of Foreign Affairs of Italy has developed over the years in a systematic way. We have done this as a country because we have very high, we believe university and research centers of Italy are of very high quality. And so they are an asset to our foreign policy, because they will, with their capacities and prestige, enable us to foster bilateral relation with many countries and offer the best of what Italy has in terms of research, innovation, culture, and so it's a pillar to which we are very much attached to, and it's a privilege to have the occasion now in Cyprus again after a long COVID parenthesis to have one lecture. And we have chosen, together with our friends from the Cyprus Institute, hydrogen as a theme, because for this year discussion, and we are very grateful to Professor Armaroli for being with us today. He had a long journey to Cyprus, and we were just discussing this, to be with us today in this prestigious location, and to discuss with us about a very promising or innovative, you will tell us better, resource for decarbonization, and something that is very high on the international agenda. I, as a diplomat, read a lot about hydrogen, but I don't know and I don't understand fully the potential of hydrogen, the shortcoming, the critical aspects of the green transition and to whatever is related to it. So I very much welcome you, and again, all of you to this interesting event. I don't want to take much of your time. I am very eager to know about hydrogen and to listen to your comments later on. So thank you very much for being with us today. And again, thank to the Cyprus Institute. I regret not to see the president, but we will have other occasion to meet and to have further lectures here in Cyprus. Thank you very much again.
Well, I have few words of introduction because when we have been asked to think about this event and to think about an event on hydrogen, I mean, it was clear that, I mean, one of the most prominent Italian experts was Nicola Armaroli. He has been, is part of an historical group working on photochemistry. I was telling Nicola this morning that I knew about this group from a friend, Cesare Silvi, who is an historian, let's say, of solar energy. And he told me about the Chamichan department in Bologna. And 100 years ago, I went there and read what was, in the papers of this scientist. And 100 years ago, he was saying that the future would have been of solar energy, and that we should develop new chemistry in order to make this possible. I mean, 100 years ago. So I said that's the right team, and Nicola Armaroli was the right person because he's really engaged in, let's say, dissemination of knowledge. Just to say a few words, I went through your profile. He's now research director in the National Research Council, and this is in the tradition of the Fermi lecture because we had the president of the CNR a couple of years ago. He is now the director of one of the most important, let's say, journals to popularize science in Italy, that is Sapere, and a member of the Italian National Academy of Sciences. He's dealing with photochemistry and photophysics, and in general to all the tools that we need for the energy transition. There are a number of prizes and awards. Just to mention, because it's close to my, let's say, I mean, the way I've been approaching science, I would mention the Enzo Tiezzi gold medal, because Enzo Tiezzi has been a, let's say, pillar in the history of the Italian renewable energy movement, and in general, I mean, addressing science from the complexity side. So it's not just science, it's science dealing with politics, it's science dealing with society, it's science dealing with people. So I will close this introduction with something that is in the profile I found on the web, that Nicola Armaroli is committed to advise people that science and technology alone cannot warrant us a sustainable future. So it's a matter of not leaving science alone, and sometimes scientists are making the mistake to think that they are self-sufficient, and on the other side, most other categories are doing the same mistake, while we have to take things together and dialogue. So I hope this will be a nice dialogue today, and please, Nicola, the floor is yours, and we will follow up with a discussion with everybody who would like to engage and talk with Nicola Armaroli later on.
Thank you very much, Fabio, for this introduction. I'd like to thank Ambassador Ferrari Bravo for having invited me here, along with the Cyprus Institute. I'm really honored to be in this Center of Excellence for Scientific Research. And, well, today I'm going to talk about a very complex topic, and I will try to make it as simple as possible, because it is something that deserves attention and doesn't deserve hype. There are sometimes hype about hydrogen, and we will try to talk about in a very, let's say, I will try to do it in a rational way, and I am available for discussion later on. So when we talk about hydrogen, first we have to ask, I am a chemist, what is hydrogen? Hydrogen is the lightest element of the periodic table of the universe, and actually it is a very great player in the universe, because sometimes we forget, but 74% of the universe is made of hydrogen, and helium is 24%, and the rest is almost nothing. So it's important. It's evident that nature makes hydrogen very important and very pervasive in a way. But if we zoom to the solar system, things are getting different. If we go to Jupiter, the atmosphere of Jupiter is full of hydrogen, molecular hydrogen, and the Earth, instead, the atmosphere is full of oxygen, lucky us that it's full of oxygen and not hydrogen, so it is full of life. But this means that molecular hydrogen on this beautiful planet is virtually absent, so we have to make it. I like to show you another periodic table that I proposed to highlight a few years ago to the European Chemical Society. And so we decided to make this table, to revive this table that was published in the 1970s, which shows a different picture. This is how the Earth is made, okay? So every element in this table is as big as it is its relative abundance on the Earth's crust or in the atmosphere. And I'd like to point out that these elements here have been magnified. This is a logarithmic scale, otherwise you wouldn't see it by naked eye. So we have elements which are plentiful on our planet, like silicon, aluminum, and others. And this is the material identity card of the Earth. So this corner of the universe is made like this. It is not all the same. And there are also colors. Green means that by the way we are using it right now, we don't have any problem for availability in the next few centuries, so we are relaxed with them. The red ones are those we are using intensively in our modern civilization, and this means that in the present century we might have problems of availability for these elements, and then you have intermediate colors. And we are making this document a live document because we are changing it and we are adapting it based on the evolution of the technology. And we have a scientific discussion behind this table that I don't want to bother you about that, but it's science-based, a science-based document. So coming back to hydrogen, you see that even on Earth, the hydrogen is abundant. The spot of hydrogen is very big. But what is the problem? That, well, it's abundant, but it's combined. It's combined with oxygen in water, and this is a planet full of water. It's combined with carbon to make methane, but you find it underground. It's combined in millions of organic molecules, organic, biological one or synthetic one, like glucose, a very trivial one. So the bottom line is that what we need is molecular hydrogen, and we have to make it. We have to make it. So hydrogen on Jupiter would be an energy source because it's there, but on planet Earth it's an energy vector because you have to make it. So you can make it starting from water, which is the most rational way. We will discuss it later on. And by electrical energy, like photovoltaics, hydropower, you make hydrogen. Making hydrogen, it means that you make chemical energy, okay? So you convert, for example, solar energy in chemical energy, in hydrogen. And once you have it, but you have made it, then you can then reconvert it to electrical energy through a fuel cell, or you can burn it, and you can have in this way thermal energy. And when you do this, you go back to water. So hydrogen can enable a circular economy because you can make it and you can use it, and then you generate water, which is the starting point again, and you go again and again and again, okay? So that's a good point about hydrogen. Can enable a circular economy. But then there are problems, and this is what I'm going to tell you about now. Let's start from some physical properties of hydrogen. Hydrogen is at ordinary conditions, so standard pressure like we have in this room and 20 degrees is as a molecular weight of, is a gas under these conditions, is a gas. Its molecular weight is the smallest one. It is colorless as a gas. It is odorless. It has a boiling point at minus 253 degrees Celsius. And it has a melting point even closer to the absolute zero at minus 260 almost. It is chemically reactive, so when you have it, it is very difficult to handle. It's not like, water, which is not reactive. It is flammable, and it is more easily flammable than methane, and even more explosive than methane potentially. And it has almost an invisible flame in daylight. This is another point of danger in handling hydrogen. Somebody says that hydrogen has a very high energy density. Yes and not. Because if you look at the density by weight, yes, indeed, hydrogen is very energy dense because its density is 3 times as much that of, for example, petrol or diesel fuel. But as I told you before, hydrogen is a gas in standard condition. So 1 kilogram of gas at ambient temperature and pressure occupies a volume of over 11 cubic meters, okay? It's a big one. So since it's a gas, the really important number is the density by volume, okay? So in that case, the situation is completely different. The energy density by volume is 4 times less than methane, and it is orders of magnitudes less than petrol or diesel fuel in volume. Hydrogen today is very important already, so we don't have to discover hydrogen. We have already discovered it in a way. But it's not important for the energy industry, it's important for the chemical industry, okay? That's the point. So we use it to make fertilizers, and we use it intensively in petroleum refining via hydrocracking, dearomatization, and so on. So hydrogen today, let's look at some numbers. Hydrogen is a very strange molecule because it is produced in about 70 million tons per year globally, per year, and in dedicated plants. So it is produced in massive amounts, but it basically doesn't have a market, which is strange. You produce something big and you don't sell it. Why you don't sell it in most cases? Because you use it immediately. What the chemical industry does is making it and use it right away in the plant itself for making hydrocracking and so on, what I mentioned before. Because it is very expensive to transport hydrogen, it can be very dangerous, as I already said. Well, unfortunately, more than 95% of the hydrogen today is made by fossil fuels, primarily methane. 6% of the demand of natural gas, 6% nowadays, is used to make hydrogen. So what I try to address people in these very days is that, listen, be careful. Natural gas is not only used for energy, for heating homes or for powering industries. It's needed for making things, okay? It's needed for making plastics, fertilizers, and so on. So if the chemical industry in Europe is blocked due to the current problems, there is a domino effect on the whole industrial system. This is something that is not yet in the public debate. Natural gas is essential for the chemical industry. 15% of natural gas imports of Germany goes to the chemical industry, okay? Remember that. And so hydrogen is used for these 2 applications, as I said, and the production of hydrogen is responsible of 2.5% of the total global emission of carbon dioxide. So making hydrogen has a strong carbon impact on our planet, so on our society. A few words about ammonia. Well, today energy uses are almost non-existent, so we have chemical uses. A few words about ammonia now. Ammonia is very important. I already asked if there is an ammonia plant in Cyprus, and there is no ammonia plant, so you import ammonia for your agriculture. Ammonium salt, of course. Well, this process of the synthesis of ammonia, which uses hydrogen, is a process that changes literally the world. And this was made by these 2 illustrious and controversial German chemists, Fritz Haber and Karl Bosch. And they studied nitrogen, the fixation of nitrogen to make explosive for the German industry during World War I, okay? But then it was realized that fixing nitrogen allows you to make also fertilizers, ammonium-based fertilizer, nitrogen-based fertilizers. And if you use fertilizers in the fields, you increase the availability of food. And anytime you increase the availability of food of an animal colony, whatever it is, even human beings, you increase the population of this colony. And in fact, if you look at the trend of the global population, look at this, any curious people may say, well, something must be happening here, you know? What's going on here? There are several phenomena, but definitely the detonator of this population explosion is the fixation of ammonia and the synthesis of ammonium salts for fertilization. And this is strictly related to hydrogen, okay? Hydrogen is linked to the increase of the human population. As I said, it is very little used in the energy industry instead. And, well, it has been used by the space industry for a long time. And it was used as fuel for launch in Apollo and Space Shuttle missions. This big tanker here that we all know, I would say everybody here has seen it, and was full of hydrogen and oxygen. And it has been used also in fuel cells. This is a picture I took myself at the Kennedy Space Center in Cape Canaveral, and this is a fuel cell on board for the production of electricity inside Apollo mission systems. So this is what is about energy and hydrogen so far, essentially space industry. But just about, I spoke about energy, let me give you a few hints about the energy transition, and then we will come back to hydrogen, right? Well, the energy transition that it is ongoing, and we have to move away from fossil fuels according to our plans by the mid of this century, is a process that has started actually more than 200 years ago. We have been, as humankind, in energy transition for over 2 centuries, because at the beginning of the 19th century, humankind was powered by wood, traditional biomass at almost 100%, okay? Then there was the first energy revolution with the use of coal. This is a percentage, of course, not an absolute value. So the coal rise lasted about 1 century. So the transition from wood to coal took 1 century. And then coal was further integrated and substituted by oil, and then it came gas, and then it comes the other technology. So in a way, we don't have to be so much concerned about the energy transition because we are very familiar with it. But there are 2 points I want to highlight. The first one is that we have 30 years for this ongoing energy transition. We don't have 100 years like here. And the other problem is that at present, we are 8 billion people on this planet in a very globalized and interconnected economy, which makes things more difficult, as we know. And we are going to be 10 billion by mid-century. So this population is still growing. So these few numbers show you the complexity of the current energy transition, which is not the topic of today, maybe next time. The world primary energy supply is this one, okay? And more than 80% is fossil fuels. And the bad news is that actually it has been like this since decades. So our civilization is more than 80% since decades. It was like this in the 80s, in the 60s, in the 50s. So this system is extremely connected to our economy, and it is very difficult to change it because it has a big inertia. We have been here for so long, okay? And the problem, as you know, is that by burning all of these fossil fuels per year, we generate a lot of carbon dioxide and we make global warming. And this is the main, not the only one, but the main responsible for global warming. So what is the situation? It is this one. Greenhouse gas emissions and warming scenario. Climate scientists tell us that we have 1.1 degrees of increase of temperature so far due to anthropogenic effects. So we have to change our path. We have several options. The option number 1 is doing nothing. This means that without climate policies, we will reach going like this to almost 5 degrees. And this is what I call the catastrophic scenario. I don't want even hear about it, okay? Like this. So the other possibility is doing what we are doing now, maybe even better, and we could reach up to 3 degrees. This is still a calamitous scenario, indeed, okay? So we have what I call the forced scenario, obliged scenario, call it as you wish, to stay within 2 degrees. So this means that we should have start diminishing emissions since 2015. We haven't yet done it yet. They keep growing, they keep growing. So, but listen, going 2 degrees, it means that if we are smart enough to take this path here, at best, the situation will be much worse than it is now. Because now we have 1.1, and it is already a disaster, okay? So our promised land is not going to the climate of the 1970s or the 1980s. It's going to 2 degrees, which will be much worse than it is now. So we have to undertake already adaptation policies. And we have to be aware that we have to rush for the energy transition because 2 degrees is already a very complicated scenario. How fast should we run? And let me give you the case of Italy. So European countries, including Cyprus, of course, have to cut by 55% greenhouse gas emission by 2030 with respect to 1990. So for Italy, this means that we have to go from here to here. So where are we now? Before the pandemic, now the situation is basically the same. We were here. So this means that we decreased by 19%. So we decreased, but not so much. So it means that going from here to here, we have to decrease by 44%, okay? So this means that we have to cut, in percentage, more than twice, okay, in, unfortunately, 1/3 of the time. This is the window, this was the previous window. So this means practically that we have to run and rush 7 times faster than before in cutting greenhouse gas emissions. I'm talking about 7 times, okay? I'm not talking about 70%, okay? So this means that having twice as much in percentage and in 1/3 of the time, 7 times. So we have to start asking if it is realistic. It is probably not, but this means that we have to run as much as possible, because anyway, we have to avoid a disaster. So what is the energy transition trends in end users? So where are we in this energy transition? If you take energy end users, you have heating and cooling, transport, and power. Well, in heating and cooling, the renewable energy share globally is 11%. In the transportation system is less than 4%, pretty depressing. Okay, I know that in Cyprus, 50% of the energy goes in the transportation system, so this number is pretty depressing. The good number is this one. In electricity, we are almost 30% globally in producing from renewable sources. In Italy, we are almost 40% already now, okay? So this is going well, and this is why we have to electrify as much as possible. So the bottom line of this data is that we still burn too much. We still burn too much. This is the essence of our energy problem, okay? We used to burn when we were in the caverns, in the Middle Age, and it was understandable. But we are supposed to be advanced civilization, and in this advanced civilization, modern one, we still burn too much to heat our building, to move, and to make electricity. And in Europe, which is the most advanced continent in the energy transition, 75% of final energy uses is obtained by burning something, okay? This is our problem. The main way out was discussed in this article by Vincenzo Bazzani and myself 11 years ago, okay? At that time, it was quite naive to talk about an electricity-powered world, I tell you. And now it is common sense, okay? Anyhow, why we proposed this, to move from molecules to electrons? Because very easy, very simple to understand. Electric machines are far more efficient than combustion counterparts. And we do have already the technologies to make, on the market, to make electricity available. And they are, of course, especially photovoltaics and wind. But now I will move again back to hydrogen, okay? Because we still need decarbonized molecules for some energy uses. We still need them for the heavy industry, in particular cement, steel, plastics, and perhaps we will see, I will go into detail on this, on heavy transport. Yes and no. I will show you why. So let's go to hydrogen. Hydrogen is the decarbonized molecules that allow us only to not stay alone with electrons, which is very good, the first pathway, but also to have some molecules which allow us to use them without making carbon dioxide. So making, handling, transporting and using hydrogen is the next part of my talk. Nowadays, hydrogen comes from methane and we call it gray. And it's a complex chemical process with various reactions. It is the steam reforming. I will just put the general reaction to not make things too complicated. So we use methane, we extract hydrogen from methane, we produce hydrogen, but we produce carbon dioxide because, of course, this carbon combines with this oxygen, and there is nothing we can do for that. The energy, the carbon dioxide is the problem, and it goes in the atmosphere, 2.5% globally, as I told you before. The energy is very favorable. This process, which is a chain of processes, is a very, after all, low energy requirement. That's why we use it so extensively. It's really a very smart process in terms of chemical technology. The other, somebody says, okay, since this is a problem, we can have blue hydrogen by confining carbon dioxide. Instead of putting up there, you put it down there. Well, it's easy on paper. It's easy on paper. And there is too much simplification on that. Too much damn simplification on that, okay? Because these are only proposals on paper, okay? 30 years of CCS has already occurred, and this is the result. This is a very effective picture by Carbon Tracker. This is the amount of carbon dioxide that we put in the atmosphere annually as modern civilization. This is what we put underground after 30 years of research, okay? And essentially, almost all of this is put in the underground in this way to squeeze old and aged oil fields to let them produce the last drops, let's say, the last barrels of oil. And then you extract this oil, you burn it, and you don't capture the carbon dioxide related to it. So it doesn't seem to be a very smart exercise from the environmental point of view. Economically, it can make sense, but probably there are other important points. So this is the situation of supposed to be blue hydrogen. It is not a zero-emission technology. Even though you can implement it, it's not a zero-emission technology. I don't have time to go into detail. There is a risk of slipping because you put it there, but nobody can guarantee that it will stay there forever. And even small leaks can have a big contribution because carbon dioxide stays in the atmosphere for 100 years. And it can generate induced seismicity. That's another problem, injecting carbon dioxide there. And it is for sure an attractive approach for the gas industry, which is not necessarily the interest of the whole human community, okay? And then the other way is to make it green, so without carbon. And it is clear that you can only make it from water, using electricity, using electrolyzers like this one, and using renewable electricity, of course. You make hydrogen and oxygen, no carbon whatsoever. And you can put oxygen in the atmosphere without any damage, or you can use it. We have understood in the pandemics that oxygen is important, molecular oxygen. Here the energy, however, is very, very, very big. That's the problem. Because why this planet is full of water? Because it is a low energy molecule, okay? And if you want to make an highly energetic molecule from that, you have to inject a lot of energy. That's very simple. Even a kid can understand that. So to make 1 kilogram of hydrogen, it requires 55 kilowatt-hour of electricity, 9 liters of still water, which can be a problem for a water-restricted country like Cyprus or southern Italy. That's a point. And you end up with 33 kilowatt-hours of heat in that hydrogen, which is minus 30% during the process, of course. So to make this concept more clear, let me tell you what it is. 55 kilowatt hours of electricity corresponds to the average energy consumption of an Italian family for 1 week, okay? 1 kilogram of hydrogen in energy terms is the energy equivalent of the consumption of an average Italian family for 1 day. So to make 1 day of natural gas equivalent, you consume 1 week of electricity. Is it clear? Okay? So that's the problem. That's the problem. Whatever you do with hydrogen, this is what you have to deal with, because you cannot make any deal with thermodynamics. Okay? There is no way of making any deal. Electrolyzers are very complex systems. There are 2 commercial technologies, and they prefer a continuous electric flow, so they work very well with hydroelectricity, and the big green hydrogen plants in the world are essentially, all of them are powered by hydroelectricity because you have a continuous flow. It's not the case of Cyprus, I suspect. And with intermittent energy sources, it's more complicated to run them. Well, electrolyzer technology is set to improve substantially over the next 10 years, and this is a great opportunity for European industry, because the European industry, if you look in detail in this machine, is strong in each and every aspect of this technology. So this is a good point. I mean, if we are able to make better electrolyzer, that will be extremely beneficial for the European industry, which has a big know-how in this direction. That's a good point. Now there is a slide about prices, but talking about prices nowadays is like talking about nothing. Anyway, I will give you the numbers before this energy disaster that we are witnessing. In 2020, the idea was the following. The price of hydrogen from methane was $1.6 per kilogram. And from renewables, it was around 6, so 4 times as much, approximately, very approximately. Now, it's unclear what is this cost, even now, not only 2030, because methane costs a lot. And the trend from renewables should be this one, so by mid-century, for sure, the green hydrogen will be extremely competitive. There is another route to make hydrogen, not with electrolyzer, but it's with the so-called direct conversion route, which is what we do in our laboratories at CNR. And regarding the direct conversion of hydrogen through photoelectrochemical systems, we prepared, along with other European groups, this roadmap, and you can download it on the internet. And we are now focused in our lab on this project to make from first hydrogen, and from hydrogen to make dimethyl ether or methanol. That's another route, but it's even much farther away than electrolyzer, of course. It is still fundamental research. Hydrogen handling and storage. How we handle hydrogen? Well, let's take a real device, this hydrogen car, the most famous hydrogen car on the market. And this contains tanks at 700 bar. 700 bar is a lot, okay, it's a lot. And you can liquefy it, but to liquefy it, as I said before, you have to go to minus 253 degrees, and this costs a lot of energy. And it's not a problem for the NASA budget, but it can be a problem for you, Fabio, for your budget to have liquid hydrogen in your house. So the energy consumption, the theoretical minimum to make this effort, is 1.4 kilowatt hour per kilogram to compress at 700 bar, and 12 kilowatt hour per kilogram to make it at minus 253. This number means that if you have a given volume of hydrogen, 30% of that energy in volume, 30% of that volume in energy terms goes to liquefy the remaining 70%, okay? And so you lose already 30% in doing this job. Again, it's not a problem for NASA, it can be a problem for you. So we have to handle it in another way if you want to do it in an efficient way. And the first way is to embed it in solid materials which can absorb hydrogen, like in pores, or chemically connect hydrogen somehow, and then deliver it by an increase of temperature, for example. Or you can really hide inside molecules, like the so-called liquid organic hydrogen carrier. The simplest one is ammonia. You can hide the hydrogen in ammonia, and you can liquefy ammonia at much higher temperature, around minus 30 degrees. But then you have to free hydrogen, and you have to make a catalytic process to free hydrogen from ammonia, and you can do it even with other more complicated molecules. Another perspective is to use, which is the same concept as CCS, to use underground, to store hydrogen underground. But then comes the reactivity of hydrogen. So if you store hydrogen underground, it can undergo geochemical processes, it can go bacterial-driven processes, and then you put 100 kilograms of hydrogen in underground, and after a few months you find 40 kilograms of that. That's another problem. It's extremely reactive. So it's not here, but of course research on all of this must be absolutely fostered and financed, because we will have probably better solutions than we have now. Hydrogen transport. I know now that in Cyprus there is no distribution of natural gas network because you are an island. But in continental Europe we have it, and it is massive. This is a transmission network, so the big tubes, the 1.2 meter tubes, the one as big as Nord Stream, okay? And somebody says, well, we have already this transmission network. What is the problem? We produce hydrogen wherever we want, and then we transport wherever we want. Easy to say, difficult to make. Because if you look globally, in terms of transmission lines, there are 5,000 kilometers of transmission line of hydrogen and 3 million kilometers for natural gas. There must be a reason for that, of course. And the reason is that reactivity and the fact that hydrogen inside the pipelines embrittle it and can be extremely dangerous. So you have to use specific steels, which is extremely expensive and so on. So if you want to use the current transmission network as a whole, you have to change basically almost everything. You have to change the tubes, the valves, the compressor, and so on. And so you have to check case by case what you can really do. It is not granted. And I want to invite you to look at this document, which is prepared by the European Authority on Gas Transport, and shows what are the complexities of hydrogen transportation and adapting the current gas transportation to that. Somebody says, well, why don't produce it elsewhere and import? Instead of making electrolyzer in Italy, in Germany, or wherever, we can use the huge solar resources of North Africa, for example, and make hydrogen there with electrolyzer and then transport there. There is a good point and a bad point on that. The good point, the advantage is that you have low-cost renewable electricity here, which is very good. And you can give a prospect of social stability to these countries that once they will not export any more hydrocarbons to Europe, what is their destiny? That's a big point in terms of social cohesion at the general level, okay? So if they produce hydrogen, they can still have something to sell and thrive on. The disadvantage is that we perpetuate energy dependence models. We are suffering from that. And we have geopolitical unknowns. Probably somebody knows that some 10, 20 years ago, there was a project, Desert Tech. The idea was to produce electricity in those areas using concentrated solar power. And this was a fantastic project, but after the Arab Springs and so on, geopolitical reasons, it stopped. And now it used to be a foundation, and now I think it's disappeared. So there is big unknowns in doing this kind of projects. So somebody says, why don't we mix hydrogen with natural gas? I don't think it's a very smart idea, because if you take the mix, you start from 100% methane and 0 hydrogen, then you increase hydrogen and decrease methane up to the opposite, 100% and 0. The energy contents goes down because we are dealing with a gas, and it is going down, and that's a problem. I mean, if you propose to a manager of a power plant to make this mixing, he's not very happy to know that the energy content of the input is going down and down. It will be desperate. I mean, it will be very aggressive with you on that. So if you use 10 to 20% mix, so if you stop here, basically, you stop here and you focus here, well, you lose only, let's say, 15%. But what is the advantage in terms of carbon dioxide emission? Minus 6%. So you make a big effort, you make hydrogen, very valuable, you consume a lot of energy, you mix it, and then you end up with minus 6%. That's not so much, clearly. So I don't think that mixing hydrogen and methane from the thermodynamic point of view is a good idea. It's probably a good idea for gas companies, and we can discuss about it, but definitely not a brilliant idea. So what are the energy uses of hydrogen? We have two possibilities. One is to use it as a fuel for low temperature applications like heating your house. You don't need it in Cyprus, essentially, but we need it somewhere else. Or you burn it to obtaining high temperatures, like those needed by steel, cement, glass, paper industries. That's a very important possibility because there are no big alternatives to natural gas. So that's a good idea on this. Here, instead, is a very bad idea, and I will tell you in a minute why. The other possibility is to use it as a vector. This is what happens in a hydrogen car with a fuel cell, of course. Why hydrogen in residential heating is nonsense? Because if you have 100 units of renewable electricity produced on your roof, I've seen many solar roofs here. Most of them are solar thermal, but also photovoltaics, which is very good. And imagine also to have an electrolyzer in the basement, okay? So you produce hydrogen, you produce electricity, you make hydrogen in the basement, and then you put it in your furnace and you get what? You get 60 units of heat out of 100 units of renewable electricity. If you do the same as I do in my house with a geothermal heat pump I have in my house, I get much better results because with 100 units of renewable electricity, I get 300 to 500 units of heat. Why? Do you generate energy from nothing? No, here you generate energy because you convert to heat energy. Here you just take the energy where it is already present, it is there, underground or in the air, and you put in your house, and it is much more energy efficient. That's why it is absolutely nonsense to make this operation. This is absolutely nonsense. The heat pump sales in the leading markets are going up, and Italy is the second country after Poland in increase in the heat pump market, and this is a very good news. Of course, hydrogen can be instead useful for daily and seasonal storage. This is the profile of a California production day of electricity, which might be similar to Cyprus. And at midday, you have a lot of photovoltaics, and part of it is in excess because they don't know how to use it. So what can you do with the red part here? Just you curtail it, you throw it away. Well, you have one possibility to put in batteries, and the other one is to put in hydrogen. And if you can store it in a good way, that's a brilliant idea, okay? So that's the very, very perspective of hydrogen on the long term. Hydrogen in transportation. Along with other colleagues, I wrote this report for the Italian government. We published it in April. So I don't have time to go into the details, the decarbonization of the Italian energy transportation system, but it can be applied to any European country. So maybe you find it interesting. There are all transportation means, all the option of powering them, and each of these square would require 20 minutes of discussion, so I don't have time. I invite you to go to this, to download the report or to look at this paper here where we have summarized the main result. Let me give you just a few hints. Let's compare a hydrogen vehicle with an electric vehicle. So, electric vehicle is, the fuel cell vehicle is an electric vehicle. So, the hydrogen car is an electric car, okay? Because the fuel cell produces electricity, put it in a battery, and then goes to the engine. And here, this is electric, this is obvious, this is a battery vehicles, but the battery is also here, smaller, of course, and the electric engine is also here. So this system here is extremely complicated. It has the 3 cylinders, 700 atmosphere, it has the fuel cell, the battery, the captation system from the outside, because you have to get oxygen from the outside and purify it. That's another complication. This system here is much, much, much simpler. And it is a closed system without any captation from the outside. It is essentially a battery with wheels. I tell you, I have had battery vehicles for 5 years, and I really consider it a battery with wheels. Let's make a comparison, a practical comparison on 2 cars which are available on the market, the Toyota Mirai and the Tesla Model 3 Standard Range Plus. This car here is filled up by 5.6 kilograms of hydrogen. To make them, you need 300 kilowatt hours of electricity. To power this car, you just need 50 kilowatt hour of electricity. If you compare the performance, this is the performance of this car, and this is the performance of that car. The mileage is lower, but even the cost is lower, not too much, but lower, and the refill cost is much lower, and most importantly, you have, in Italy, you have almost 30,000 public recharging stations, plus your garage. I do it in my garage, powered by my photovoltaic, and there in Italy, you have 3 recharging stations, not so much. So for light-duty vehicles, and you compare battery electric vehicles versus fuel cell, the bottom line is this one. The starting point is the same, renewable electricity here and here. This is battery and this is hydrogen fuel cell. The end point is the same, an electric engine, okay? But in between there is a huge difference. Here you have just the transmission line, and then you power you charge your battery, and then it goes. And then here you have to make hydrogen, to compress, liquefy, transport it, destroy it, because then you have to make electricity. And so what is the point is that here the efficiency from here to here is 70 to 90%, depending on your network. Here is 20, 35%. So in a way, to run a given range of kilometers, if you have a battery car compared to a traditional internal combustion engine, it consumes 4 times less, okay, the battery car. In the case of hydrogen, it consumes 3 times less. So the difference between the hydrogen and the internal combustion engine car is not that big. So there is an improvement, but not that big. So this means that going from internal combustion engine to hydrogen fuel cell car is not that a big gain in terms of efficiency. If you go to heavy-duty vehicles, the situation is more complicated, as discussed in the report. You can have hydrogen, you can have batteries, you can have biofuels, you can have synthetic fuels. I don't have time to go into these details. Let me just tell you that there are physical and materials limitations. Imagine a battery for a truck, big, so much, big amount of lithium. Imagine a fuel cell for a train, very big one. And there are infrastructural problems, high power charge station, non-existent hydrogen station, and so on. And most solutions are not available now, like the hydrogen airplane. If you look at the public transportation and you are a public administrator, in principle you have 3 choices now. You can do that. You can have an hydrogen bus in your city, you can have a battery bus in your city, you can have a liquid biofuels or synthetic fuels. All of them are available, okay? But the trends of the last few, I would say even weeks, are the following. Battery option tends to prevail. The case of the city of Montpellier, they had a contract for make a hydrogen bus fleet, and they gave up, and they decided to opt for battery because it is much cheaper. For trucks, battery or hydrogen. The same here. I invite you to look at this paper by this German author, and again he says that there is little room even for trucks to become hydrogen powered. In the meantime, however, We have already electricity transportation means for freight, which is trains, of course, so modal change, and even in perspective, the possibility of electrify the motorways, and this is discussed in the report. What about trains? There are thousands of kilometers in Europe of non-electrified lines. Again, there are examples across Europe of hydrogen trains, even of battery trains. And this is last week news that I wanted to highlight here by a hydrogen website. And in Baden-Württemberg, they decided that hydrogen is not a good idea even for train because it is too expensive, so they are going to give up. So again, it seems that the hydrogen in transportation is not getting momentum. What about ships? As long as you have such a small ship, you don't have problems. But when you have a big ship, you have problems. And you know, you are an island and you know what are big ships. And this is, if you go to marinetraffic.com, you will see that this is the present snapshot of the big ships traffic around the world, cargoes and the cruise. And so, due to this picture, I decided to make a small calculation. I considered, you remember the ship that had this problem on the Suez Canal last year. And this ship is very big, and it takes 30, 40 days from going to Shanghai to Genova or Rotterdam. Long trip. How much does it burn? A lot. Just for one trip is 9,000 tons of heavy fuel oil. 9,000 tons, okay? Multiply it by the ships I showed you in the previous slide, just to have an idea, okay? So if we want to use hydrogen for this ship, it's not possible. But let's forget about that. You need another ship, okay? If in energetic terms, you would need 3,000 tons of hydrogen, and someone might say, well, very good. So you have less fuel. Well, no, because the energy density in volume of liquid hydrogen is very small. So actually you need for this 3,000 ton a tank which is twice as big as it is for this ship here with the heavy oil fuel. So that's another technical problem, okay? You understand that how complicated is the story. To make this green, forget about the energy you need to keep it at minus 252 for 30 days across the ocean at the equator. You need 150 gigawatt hours of electricity. Is it a lot? Is it a little bit? It's a lot. To give you an idea that it's a lot, I took the largest electrolyzer in the world, which is based in Fukushima, not by chance, powered by photovoltaics. This is a 10 megawatt electrolyzer in Japan, powered by this big solar field, 18 hectares large, 26 football fields, okay? Well, to power that hypothetical hydrogen ship with this machine, the point is this: a plant like this must work 3 years consecutively without stopping ever for one refill of that big cargo, okay? So you can understand that that's not trivial to handle these problems. So I think that at this point there is the difference between an energy and an ecological transition. What I mean? I mean that if we want to make an energy transition, we have just to replace one diesel ship with one alternative fuel ship. But here the problem is different. Since it is so complicated, we have to make an ecological transition. Our target is an ecological transition, not just an energy transition. So the question is, shall we partially reconsider the delocalization of the industrial production? Because since you decide to produce everything somewhere else, typically in China, because it is cheap, because it is cheap to transport it, it has been true for decades, it is no longer the case now, well, you can do that. But if you want to make an ecological transition, what you have to change is the system. We have made an unsustainable freight transportation system. This is the very truth that we don't want to to consider. This is the point. Hydrogen aircrafts, well, we use a fantastic liquid fuel now, the Jet A or Jet A1 kerosene. It has a very high energy density. It is liquid until minus 50 degrees up to 10 kilometers up there. And it allows you to make non-stop flights for over 20 hours all across the planet. And it is very hard to replace kerosene, very hard. We have discussed it in the report. So it is very unlikely to replace it with batteries or hydrogen, even in the long term, especially for long-haul flight, of course. And there are various reasons. First of all, the gravity, if you wish. Realistic solutions is liquid fuels from waste. So we will continue to use liquid fuels, but we have to do it differently. And to make liquid fuels, we require carbon and hydrogen. So making hydrogen will be very important to make sustainable fuels. But you need also sustainable carbon, and this means essentially waste, agricultural waste, food waste, and municipal waste, and so on. And then you can undertake this process via essentially Fischer-Tropsch. At present, you can see sometimes in the airport this kind of green trucks, but you can mix only 50 to 50% ratio with jet fuel. This is the regulation, international regulation. And after almost 30 years of sustainable available fuels, listen, we are using them in less than 0.1%. So basically nothing. And finally, I want to switch from machines and sectors to countries. So recently, last year I published this paper with my colleague, Andrea Barbieri, and we thought, what about Italy, which is an industrial country, if we want to make something with hydrogen? Make what? See you in a second. Let me tell you first the scope of the analysis. We wanted to identify minimal green hydrogen uses for Italy by the present decade, and to assess the related electricity, electrolyzer, water, and land requirements to make it. And finally, to evaluate the results we obtain in the light of the EU renewable electricity target, irrespective of green hydrogen targets. We made several assumptions from literature. I don't want to bother you on this, but these are the assumptions of our paper. And for the sake of simplicity, we only considered photovoltaics because it will be the dominant renewable electricity in Italy. We have little wind and some problems with offshore winds. So we spotted 3 green hydrogen targets for 2030. The first one is to make green the gray hydrogen we make now. And we would need this amount of hydrogen per year in Italy. The other one is to make green steel. This is made in Taranto, and this would require this amount of hydrogen to make it green in the blast furnace. And finally, according to the documents of the government, we should cover by 2030 2% of Italy's final energy demand, 2%, little amount. So if you sum up all of this, you end up with 1.6 megaton of hydrogen per year for Italy for doing this, and this. Is it a lot or not? Well, to make it green, you need 85 terawatt hour of electricity per year. Practically, what does it mean? 10 gigawatt of electrolyzer capacity only for Italy. Since the target for EU is 80, around 80, yes and no. We are one country, but, well, maybe feasible, maybe not, but that's not necessarily an obstacle. Green, orange phase. What about surface? If we want to make it with photovoltaics, the PV surface would be this one, which would be big for Cyprus, but not for Italy, because it is less than 1% of unused or abandoned land. So it's not a problem. It's a green phase. What about water? In absolute terms, it seems to be a big amount, 30 mega cubic meters of fresh water. But after all, it is 0.4% of the total industrial water used in Italy. So it's not prohibitive, definitely, green phase. And the last point is how much photovoltaics should you need? Here, the phase is red because you need 75 gigawatt of photovoltaics, which is 3.5 times the present deployment of photovoltaics in Italy, only for these dedicated hydrogen users. And in Italy, we had an annual installation rate which had a big jump in 2010-11, like this. And you see the global deployment. So we had the big jump here. So we should keep this jump. We should have kept this jump for the next 10 years. But we decided, I will not go back to the political reason, but I don't want to comment on that. We should replicate this exceptional trend for the years to come, since we stopped it for 10 years. So, meanwhile, irrespective of the hydrogen production, Italy, as Cyprus and any European country, has an renewable electricity target. We are at 36% in Italy, and we have to go to 66%, two-thirds, okay? So we have to move from 116 terawatt-hour to 200 terawatt-hours, and possibly even more. So to reach the target, this target here, we need 80 terawatt-hours without green hydrogen. So we need other 70 gigawatt of photovoltaics. That's a lot, just to make what we have, we are about to make. So summing up, to make the three selected uses of hydrogen, you need this. To make the green electricity according to EU targets, you need the same, essentially the same, okay? So total is 165 terawatt-hours, which is about 50% of Italy's present annual consumption, okay, to do these two things. Can we do both in 10 years? Is it realistic? I don't think so. So that's why we concluded the paper saying that if you go back to our three uses, you have to spot priorities. The highest priorities goes to make green what we already make gray, of course. This would be great, but medium priority, and this is the lowest one, definitely. We don't think about that. First electrify, first put heat pumps. So in the next decades, first electrification, then green hydrogen. And green hydrogen starting from the next decade in hydrogen valleys, possibly, maybe even in Cyprus there will be an hydrogen valley one day, maybe not, which means local districts of various size that integrate producers, distributors, and users, which can be transportation and even industries. So I am at the end. I want to leave you some take-home messages. Conventional production methods of hydrogen are efficient, very efficient, but unsustainable. Green hydrogen is the only sustainable option. Hydrogen has long been used by the chemical industry and the petrochemical industry, so we know it, we know how to handle it, but using for energy is a different business. And today we work to harness the potential of hydrogen in the energy sector. It's another sector, and so we have to reinvent many things. Many issues, physical properties, we cannot negotiate with them, energy-intensive production, transportation problems, storage still not at a very advanced level. It is a valuable resource that must be used only when there are no alternatives, because it is too valuable. Definitely no for light-duty vehicles. Yes for heavy industries, definitely. Perhaps for heavy-duty vehicles, perhaps. Hydrogen is a great opportunity that deserves great attention, but even greater realism. I know that there are not many Italians here, but if you want to deepen this knowledge on that, I wrote 3 books on this, and the latest one was issued a few weeks ago. I have also a couple of books in English, if you want, and I am on LinkedIn to discuss only this kind of scientific arguments, topics. And somebody may ask me now, can we make it? The energy transition. Well, I don't know. I really don't know. But I am a scientist, as most of you. And our duty is not to predict the future. Nobody is able to predict the future. Every detail of the energy transition is unknown, essentially. But our task as scientists is to make it possible. So let's work strong together and let's make it possible. Thank you very much for your attention.
Thank you so much, Nicola, for this very comprehensive approach to the topic, and I mean, I will just take your point that we should be in this approach to hydrogen specific, because what you say is that we have to understand where it works well and try to invest strongly in the direction where it works well. I think this is the main point I got from it. We have time for conversation, for dialogue, so this is for this reason. You want to start?
Sure, why not? First of all, thank you very much for indeed a very comprehensive presentation. Thank you for coming to the Cyprus Institute. This is a topic which is indeed very hot and very relevant to what we do. I have one remark and one question. The remark has to do with a slide that you showed on the use of curtailed PV production, curtailed meaning the one that is not used. And you said that this is a bright opportunity for hydrogen use. I think that this is actually not really the case, because the economics don't really work out that well. Even in this case, even if this electricity appears to be unused, the cost of the electrolyzer, if you account for the fact that it will be used for very few hours per year, actually makes it the hydrogen produced more expensive than if you had a dedicated facility just for hydrogen itself. That's the first point. And the second one, one that you didn't touch on your presentation, is what your position is on the use of derivatives of hydrogen for the shipping industry, especially ammonia, which you talked about a lot in your presentation, but how would that work as a fuel for ships and not hydrogen itself in liquefied or compressed form? That's the 2 points.
Thank you very much. I fully agree with your remark. There would be a cost if you use only that small part, you know, of course. And the problem is, if we want to decarbonize the system, this will have cost. And probably this is one of the costs that we have to pay if we want to have a molecule that is decarbonized, because for some uses it will be necessary, even in the future. So we will have an electricity system which will be much cheaper. As I told to some people here during lunch, I am energy independent. I spend zero, well, less than zero. I earn money by producing electricity in my house. So I could, let's say, pay some bill for keeping that facilities running, even though they are not economically sustainable in 20, 30 years. So that's probably the case. So since it will be so different, even from the economic point of view, I believe that we will be able to pay for them differently, okay, in this new system. The second point is that, yes, we could use other fuels or vectors to power ships. One is ammonia, for example, and there are plans, if you look at some companies' plans to use ammonia. Methanol in some cases is already used. But again, when you look at the numbers, they are really scaring, because if you want to make methanol, you need to have renewable carbon, as I said. So the amount that we can produce by waste of any sort is incompatible with a deep decarbonization of that. So I'm not very optimistic about this solution, at least in the short term. But of course, this is something that we have to undertake. Ammonia is another problem. It is used intensively by the chemical industry, but it is used by educated personnel. So it use it extensively in ports, it's going to be a problem. If many European ports are inside the cities, okay? So having huge tanks of ammonia in these ports, which are, I think about Genova port, which is within the city, for example, that would be a very complicated task. So you should make a facility farther away, and even in that case, the cost is extremely high. So, well, there is no doubt that the big problem of the energy transition is ships and airplanes, and there are no right-away solution that we can have. And somebody says that, well, this is the only case in which it makes sense to use natural gas, so LNG-powered ships. essentially no. We have to stop using fossil natural gas. That's the problem, and we have to be well. We have to be convinced that natural gas is at the end of its glorious cycle. Okay, so making an infrastructure now of liquid natural gas ships would be a big stranded asset in 10 to 20 years. So we would make it now, and then in 20 years we can't use fossil natural gas anymore. So why we did it? So that's another big issue. So you see that it's very complicated to find alternatives, and I think that the first one that we indicated also in the report is technological advancement in efficiency of ships, which most of them are very old. For example, there is substantial room for increase the efficiency by wind assistant cruise, which is something which is being implemented in the most modern ships around the world, even oil tankers nowadays. So materials for ships and increase of efficiency is the first one, the most reliable and the most realistic one. And then for alternative fuels, the situation of the ports, the situation of the availability of alternative materials is little. So on that, it's really a big question mark still.
Thank you for the great talk. There is a strong discussion nowadays about storing the energy, mostly electricity, coming from what we call renewable sources. Renewable sources, which are mostly, photovoltaics or wind generators. So there is a strong discussion on when or if we should use batteries for storing this electricity, or if we should convert it to hydrogen. Now, if we consider the economics of that, of course, the battery is a solution, let's say, that is obvious. However, my eyes were, let's say, into the graph on your second slide, where you saw how abundant are the different elements in our planets, and you actually confirmed that these rare earths, like lithium or other materials, are not abundant. I thought, if I remember correctly, they were in the red side of the scale. So I would like your comment on that. If, for example, even if storing with hydrogen is more expensive, but if it's more sustainable in longer periods.
Yes, that's a topic that I like very much as a chemist, as even the promoter of that table. And I lecture on that, but that was not the topic of today. Let me start with a number, just to put things, just for some thoughts, okay? Last year, the combined amount of lithium, cobalt, and rare earths that were extracted from our planet was 0.5 megatons, okay, 0.5. The amount of oil, coal, and natural gas that we extracted from this planet was 15 gigaton, okay? So we are correctly concerned about availability, but nobody tells us that we are extracting this huge amount of resources from our planet and we are destroying our climate. Let me first say this, okay? Which doesn't answer to your question, but think about it, okay? What is the difference? First of all, I think that we are normally thinking about lithium-ion batteries. Well, saying lithium-ion batteries says only a part of the story, because there are different types of lithium-ion batteries. Both in my car and in my house, I have batteries without cobalt, for example, lithium iron phosphate, which are less material intensive and very robust, by the way. So there are already progress in the implementation of large-scale lithium-ion batteries, but you still need lithium, of course. There is great progress in sodium batteries. So for stationary applications, I think that in the next 10 years there will be an expansion of sodium-ion batteries, and this will decrease substantially this problem, because sodium is everywhere. You have plenty of sodium even in Cyprus, yeah, the sea, we do in Italy, you know. So, and we can solve two problems. We can eliminate salt from water and at the same time obtain materials for batteries. And so there will be a technological innovation on that. Second, there are also other technologies which are ramping up, like carbon dioxide so-called batteries, which are not batteries, are just they exploit the compression and liquefaction of carbon dioxide. There are ocean solutions. There are many other solutions. So I'm not very concerned on the availability of lithium, honestly, and also because they are looking for lithium everywhere and they find lithium everywhere. If you add to this that there will be alternative solution relatively soon, I'm not very concerned about that. What I'm more concerned about is the following. Here you have lithium, here you have the battery. As a citizen, you don't care about lithium, you care about battery. You want to go and buy a battery, a mobile, stationary for your photovoltaics. And in between there is a long story. There is extraction, refining, obtaining permit for extraction, refining, making components like cathodes, anodes, separators, blah, 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 and then assemble them and then sell them. So I think that the problem in the energy transition is not the availability of most elements and most metal, not all of them. Some are really in danger, but most of them, lithium, I'm not extremely concerned about that. Is, will the industrial system will be fast enough to find lithium and make batteries? Because we are in a hurry. We have to run 7 times faster, okay? That's what concerns me a lot. It concerns me really a lot, because we have to hurry up, and in order to make this, you need cooperation. There is a slide that I love to show, I didn't have time to do today. If you look at the planet Earth, how it is made, and this is a matter of diplomacy, by the way, the resources are concentrated in some parts, you mean. Oil, we know where it is, from Siberia down to the Persian Gulf. Rare earths are in China. Lithium is in South America and Australia. I could continue. They are spotted. So there is no way to make the energy and the ecological transition by fighting. I mean, there is not a single country that have all the resources needed for the economic transition, for the ecological transition. So we have to cooperate. There is no way out of that. But what's happening now, especially in the last year or two, it's exactly going in the opposite direction. And this is of extreme concern. So going back to your question, I'm not concerned about the availability of resources in this beautiful planet that we have as a gift. I'm concerned about the human stupidity in trying to solve this problem by fighting each other.
I think, but can we solve this problem? You know, we can be peaceful, cooperate, we can have better batteries, we can stop moving goods around the world. Will this be sufficient to reduce our carbon emissions to the targets in 2030?
No, we have to consume less.
Yeah.
There is no way. I mean, there is no room for 10 billion people to consume as we did. As a scientist, I've been invoking my colleagues to make meetings online, not always, because we have to meet, okay, for many years. And they was ridiculized because we wanted they wanted to meet by person. We don't need to meet by person. You don't need to go for a meeting in London for 1 day. I did it many times. Yesterday, when I was in Rome looking at the billboard there, I looked and I said, probably I was in 90% of the cities listed in this huge display. And I felt really guilty of how much myself, despite I They give these lectures, how much carbon dioxide they made. And we have to travel less. And I think that the next generation, I'm thinking about my children, they have to travel less than we did. And for sure, the solution is not switching from, let's think about cars, from 100 cars internal combustion engine to 100 cars battery. That's not the solution. Even because this system is not a transportation system, it's a general collapse. You don't go anywhere sometimes, you know. You have streets, I don't have to convince you about that. So in our report for the Italian government, we wrote that Italy, which has the second car ownership in the world after Luxembourg, the number of cars in Italy has to go down from 40 million to 24 million. This is what we say. Because there are too many cars and they don't travel too much and not used enough, so we have to use more smartly the cars, and we need to have less cars. And since the human population is moving towards cities, we have the opportunity to implement public transportation. Somebody says that the rich country is not the one that allows poor people to have a car, but allow the rich people to have public transportation. And I think this clarify the concept.
Just one question, Professor. It was very clear and very appalling because I connect to the previous question. How much money do states need to go for green transition and support households? And because it's clear from your presentation that it's affordable for big companies with big revenues, but for average households. And I think also about landscape. We are Italians. You spoke about photovoltaic panels, but we are not always in a position to install photovoltaic panels on roofs and on our beautiful landscape. So it's a very painful trade-off between energy and our roots. And I'm also thinking of Cyprus as a small island. Shall we cover Cyprus entirely with photovoltaic panels? And then where do we go?
No, the good news is that I didn't show the number. If you look at the numbers, the amount of surface that you have to cover with photovoltaics is really minimal with respect to the energy need. It's impressive how little it is, really. For example, in Italy, if you want to power in principle 100% with photovoltaic, which would be completely stupid using one technology, just to say, you need about 2,500 square kilometers, which is not that much because you have a covered area in Italy which is much bigger. So you don't have to cover any field, agricultural field. You have plenty of roofs on warehouse, on industrial plants, and wherever on buildings. So there is no problem on that, really. Well, in cities, I talk about my own story. Okay, I live in a small village which is a historical city center. There is a 14th century castle, which was established by a family coming from Cyprus, by the way. Let me close the Isolani family. And that's the Isola means island in Italian, okay? So they call Isolani because they came from here during the 14th, 13th century. So it has a historical value. It's not Siena, but it has an historical value, and the local municipality allows you to put them on the roof. When I see my house, I don't think that I devastated the landscape of my small town, and I think that Italians and public administrations have to consider that the alternative to extensive photovoltaics, not necessarily in Piazza del Campo in Siena, for example, okay? But not all of Siena is Piazza del Campo, okay? And we have to be more open, and we have to consider that the energy transition also entails a change of our landscape. Let me tell you this, if you go in the countryside, at least in northern Italy, and you try to make a photo without any electric line or infrastructure, is impossible. But we are used to it, and nobody complains about that. So, and we need electricity, and nobody would give up with it. So we have to be open also to change of some of our landscape, which doesn't mean to devastate it, to change it, okay? Yeah, yeah. Yeah, sure. Concerning, you asked me another question maybe at the beginning? Okay. The economic point of view, you have to go case by case, of course. What is clear now is this number. The money that we have to spend doing nothing, leaving things as they are, business as usual, will be much more to repair the damage of climate change than making this, okay? So this is not only, let me tell you about my own story. I have this energy independent house. I don't feel, I spend all of my money, my and my wife's money, okay? But I feel that I didn't spend money. I made an investment for me, for my kids, and for my grandchildren, okay, in the future. So it is not only spending money, it's make an investment for you, because now I don't have an electricity bill. My winter will be much more easy than most of the Italians' winter, okay? And that's an added value. And I will leave a house which has a value. Most of the houses nowadays has little value due to this, less and less. And so let's look at it not only as a expenditure, but as an investment. Of course, the government has to help on this. And I think that now the government gave 150 euro to Italian families for the bills. That was the last amount of money that was given. I think that if they give this 150 euro to buy a plug-and-play photovoltaic to put on your balcony and to attach to the electric line, which can be done in 5 minutes, would have been a much better investment. So let's try to make investment and put money to this, because in that way we have solved the problem, almost nothing basically, given the current level of electricity and gas bills, for a few days. In that case, we would have helped it to produce electricity and to get rid of this problem. So there are plenty of room for economists to think about what we can do, and there is a way to better spend the money everywhere in the world, I think.
Thank you very much for the brilliant presentation. And actually, every time that we hear this presentation, the feeling of urgency is stronger and stronger. Just a comment related and question related to this last economic point. You mentioned a couple of concepts that I fully agree. The first one is demand. We have to ask ourselves why we use energy, for which reason, and start understanding whether this is correct. Topic like justice, equity are important in this regard as well. And so, for example, we have to rethink the way in which we have our life. And at the same time, you also mentioned international collaboration, and find a way within this world that can work out. So the question is, do you think that carbon emission-based taxation might be, let's say, an old century concept? So the scheme is exactly like other things. We might need some calculation methodologies, agree on how to make calculation. And would this be a trigger to go towards the right direction? So when a screw from China will cost double than someone done in Limassol, would this be enough or not?
Well, I'm not an expert in energy economics, but for sure the fiscal tool is the one that will change the world, okay? The world of energy. Because nowadays, still, these are data from the International Monetary Fund, 5 trillion euros are given, 5 trillion euros, or dollars are given, are the same now, for energy subsidies to fossil fuels, direct and indirect, okay? So if this amount of money can be redirected, otherwise, that can make a difference. So, of course, sure, indeed, these are instruments that has to be implemented. Sometimes they are not popular. They are difficult to implement because the industrial system, the big oil, okay, let's call it by name, is against that, which is not surprising. I don't think it's a scandal if they oppose to that. It's their business. problem is that if in the present system is the state and the governments that have more power or the big oil and gas companies, okay? This is the problem. Because, you know, until it is allowed, and it is, because we are in a free market, that they make a profit, they will continue to look for new oil and gas fields. But we know as scientists that the oil and gas that has been already discovered is enough to fry our planet, okay? So they should stop it. But the question is, are the government strong enough to allow this? Unfortunately, not. So this is the problem. So what is a possibility is that these companies will be nationalized. I don't think so, this will happen. But if the climate crisis gets worse, and there are indications that it's getting worse and worse, there could start even social unrest, and that could make a big difference. So I don't want to predict the future, as it is written there, but we are in a very dangerous moment now. And I'm not sure that these companies will be allowed forever to make their own profit, because their own profit is against the interest of humankind. And we have to be very clear as scientists on this.
I think we have to close. Really, I understand that it's, can you discuss later in the, because we have this.
I can stay here for hours, I love to talk about
Yeah,
it.
I would keep it, but as we have then to move to the next, event later today, so we have some refreshment, so we can use this time to go on with the discussion. Thank you so much.
Thank you.